So hopefully we are live. Hopefully, let's see. I'm just going to check the watch page, see if it comes up. Yep, excellent. We are live. Better minimum. So we are joined today by Life is Short, or as he prefers to be called, Travis. And we have Chris, Red Pill Philosophy, both of them in the house today. Everyone want to say hello?
Hey, how's it going? Thanks for having me, Ranty.
Hey, what's up?
Yeah, you guys are absolutely rocking it right now. Both for different reasons. Red Pill with your observation, which was absolutely sensational. I have to say, I have used it several times. And also that you actually went live last night and took on the Globe Heads. You had the usual crew that used to come in and frequent Nathan's Flat Earth debates. They all descended in mass to try and bring you down. I haven't watched the end of it though. I don't know how it concluded. Do you want to tell us what happened there?
Well, I mean, even Soundly was in there. I think Red's Rhetoric even joined, but he joined for like 3 minutes and then said one sentence and left, unless that was like a bot version of Red's Rhetoric. But yeah, it was a big circus. I was kind of bored. I'm like, let me just try this out. Let me try this Nathan Oakley style open debate format out. So I put a public hangout link, went live, and a massive circus ensued. A bunch of globetards came out of the woodwork. We had Soundly, we had Red Rhetoric, and we had Gem Panda, which apparently is a notorious troll over at the Nathan Oakley debate. And yeah, it was just 7 versus 1. It was just 7 globetards basically just jumping in and ganging up on me. And they love to talk about how flat earthers are rude and they need to be moderated, and they love to talk over everybody. But I mean, it was 7 of them basically trampling all over me, and I think I did pretty well considering it was a total shit show in 7 versus 1. So yeah, it was fun. It was great.
It was good to watch. Like I say, I'm about 50 minutes in, and I could see the way it was going down. I could literally see how it was going to end up. You could see them joining one after the other, Even PMARS joined, and it was like, oh no, this is really going downhill now. And yeah, I had a feeling this is how it would end up. So I think I left a comment and I basically said, this is basically what they did with Nathan Oakley originally. And there's a reason why they don't go in Nathan Oakley's anymore. It's because
that's what I heard. That's what Nathan, I heard him mention that. He's like, it used to be that way back in the early days. You'd have a bunch of Globers and they would be trampling over you, speaking over you, making fun of you, just mockery and just this douchebag behavior. And near like about halfway through, we started getting into the angular resolution argument, and I even brought up Life is Short's incredible 3.5-hour epic presentation on this very topic, and they were trying so hard to deflect, so hard to deny. And at the end, they kind of had to concede. They're like, okay, everybody needs to go and research this topic more. Everybody, and I put the link to Life is Short's video in the chat so everybody could go watch it. And so that was kind of like the thing. Everybody needed to go home and study angular resolution, study Life is Short's video. And so that's kind of where it left off.
Yeah. Hey, thanks for that, by the way, because now I have like all the people came out of the woodwork to all the comment section is just kind of crazy. So I'm trying to respond to everybody, but it's a bit of I think it's like 300 comments so far. I'm just going back and forth on everything. But
wow, I think I said to you, I said this is great. Would I be able to mirror it? By the way, expect a lot of trolls. And, it's blown up since then. And that was a really great way to bring in Travis. Yeah, how long did it take you to put that presentation together? 3.5 hours. Come on, be honest.
Yeah, I'll be honest. So like the thing that kind of triggered the whole thing was Chris is when he had those the compression of those buildings of that condominium complex, and how those floors were squished at the bottom, and Nathan had been talking about this whole effect of things getting squished and not becoming visible, and I was just like, man, there's something to that. And then I did the whole flashlight on the ground experiment for myself, and it was just kind of an eye opener that something was going on here. So it was around Thanksgiving. I just decided I'm going to put something together. And so I just started getting out pieces of scratch paper and trying to figure this thing out. And I'll tell you, man, I went through a lot of versions of kind of how this may play out, because there's a lot of issues between what's exponential and what's linear, right? And so my first versions were like, we're seeing something exponentially, right? Exponentially drop off, and that's how it's getting smaller, and blah blah blah. And so I did my own kind of little mini perspective experiments, with the doors and the hallways and things like that. And I'm like, it's linear. Everything we see is a linear relationship. And so that kind of got scratched and thrown out, and one thing just led to another. So it took me from about a month to kind of get all the slides together and everything. And I threw out about, I don't know, 80% of all the slides I'd made. It was kind of crazy.
Wow.
But yeah, so then I published the first one in December 30th, I think it was, or somewhere around there. And then I got a lot of questions from it, like, hey, what about this and what about that? And so I started to see that maybe those points weren't very clear. And so I decided to break it up into 6 parts and just kind of explain some of the questions that people were bringing up, maybe in more detail. And that's how that kind of came out. And then when I was doing that, Chris had that footage in January where it was like a crystal clear day, where there was just no waves, there was nothing. And the water temperature, I looked it up when he was posting it. He posted it like, and within 8 minutes I had saw it, or for whatever reason I was on at the same time, and I just started going through it. And so I was looking at the water temperature that day. It was 70 degrees down there, and it was 70-degree water temperature. And essentially there was just no refraction at all. It was like a perfectly crystal clear day. And the stuff that he was able to capture from that day just to me made the baseline. Like, that's the baseline vision, and everything should be compared to that. And so then I noticed that there was this tree in the foreground in all of his shots where he was taking the compression footage, showing all the floor compression. And so I took that tree. That's going to be my marker, of where level was. He was at the same height for all those observations. So
yeah, do you want to tell us a bit about that, Chris? Because it seems like you do go to the same point, to the exact same spot. You're a creature of habit. You're a bit like me. I go to the same spot every single time, same spot on the rail. Doesn't make, I'm always doing my observations from there. Does it feel like that it's for you? You've got to set the camera height at the same, the tripod's got to be the same height. You've got to set it in the same position.
Well, the thing is that the tide goes in and out right around that area. So some days the water is really is a bit higher up, and other days I can walk maybe 80 yards out because the tide descends, and I could actually walk along these little. It's like an elevated little rock formation that stretches out pretty far out, and my intention is not necessarily to be in the exact same spot every time. But that's, really my goal is just to get far out enough to see the lighthouse, maybe to see that balcony building, which you guys have seen oftentimes shows that obvious compression effect. Sometimes if I'm really lucky, the tide would be so low that I can walk across that elevated rock formation so far that I can get a good enough angle to see buildings as far as North Miami Beach. And I did upload a video like a week or so ago with footage captured of buildings about 24, 25 miles away from where I was standing. So yeah, it's not about necessarily getting the exact same, because to be fair, I'm not even that precise necessarily. Like, I'm not Dr. John D with freaking tape measures measuring how high I am off the floor. Like, I'm roughly 6 feet above the water. I mean, I'm pretty much always right there on the water's level. And it's just what I end up capturing. And so it's been pretty interesting. But yeah, it's always variable out there. It's very fascinating.
Yeah, but I mean, what you end up seeing though is that when you have the bottom line is that when you have more of these refraction phenomenon, right? Like the more compression, the more apparent, the more inferior miraging. When you see more of that, the apparent horizon is much lower than when he shot that great footage that one day. And so, you know, I was able to use that tree, I guess, in the foreground, which is in every single one of his, well, not every single one, but most of them. Maybe a little bit left or right, it doesn't matter, and maybe a subtle height change here or there doesn't. I don't think that matters very much.
Yeah, and the tide change is not much. I mean, it's, you know, I've never directly measured it, but, you know, I mean, it's not, I mean, even though the water can drop, you know, into the distance by maybe, you know, like 30, 40 yards or so. I mean, I could be walking out pretty far out there when the tide is really low. It's a gradual descent. So I've never measured exactly the difference in actual height, but I would say it's probably not that much, honestly, because it's a very gradual descent as the tide goes out. So,
all right, and then and that's only one part. So the other part is like Ranty's time lapse footage. When this one day he took a time lapse, and well, I don't want to get too ahead of myself, I guess, but essentially your time lapse footage was a real head scratcher for me. And I was just kind of skimming, and I saw that you on another video did essentially the same observation, but you did a height change, and you went from a 4-foot elevation to a 9-foot elevation to about a 14 or 15, whatever it was, elevation within a short amount of time. And versus your time lapse footage where you set your camera down 4 feet and you just let the tide roll in. And I'm looking at these photos and time stamping them and everything, and I'm like, they're exactly the same. And it kind of I guess threw me for a loop for a little while. I was like, how is that happening? You know? So anyway, I came to the conclusion that a lot of all these effects, this is an emission refraction phenomenon. This is upward refraction. There's, you know, and so I just started diagramming it out, and like that should be how it works. And then I started looking at observations, and they matched what was going on. And then I took John Dee's stuff, and where he's done, you know, 100 however many plus hours of laser and telescope observations over water, and always seems to have emission refraction occurring.
So one thing I would just like to say, I mean, we're not going to go into this, obviously, but you do come from a physics background. That's all I'm going to say. You have looked into this. You've followed the debates. You've seen what's been going on. But don't you find it strange that both in Red Pills and my own footage is where this blockage, because we do see blockage, you know, things does have blockage at the bottom. Not all the time. Don't get me wrong, not all the time, but we do get blockage. That it always seems to be similar to what the curve calcs would be.
Well, that's so. Yeah, that was my other point, was that I wanted to incorporate refraction and diffraction into a calculator, because it seems like people need a calculator for some reason. So I did some. It's very preliminary, I guess, but I put together a calculator that seems to be actually kind of accurate. It's kind of weird, but it takes into account, you know, diffraction and refraction. So anyway, I don't want to get too ahead of myself. Let's see here. Am I screen sharing at all?
Yeah, I believe you are.
Okay, where it says summary of parts 1 through 4.
Well, I can see it on the Hangouts, so I think it's definitely popping up live. Let me double check real quick. Let me refresh the live feed. Yeah, it's popping up here. Yeah.
Okay. Let me go back one, actually. So a lot of people like, hey, you put a Bible verse at the beginning, and I'm tuned out. And I don't know. I just this is it's kind of a profound verse for me. So the tree of life argument to me is it's a very underappreciated, I guess, way to look at the world. So it's something spoken of in Genesis that it's guarded, and it's not spoken of again until Revelation. And within the entire text of the Bible, you essentially see attempts for, you know, man's attempts to climb the tree on their own, and a kind of a man's attempts to man as God kind of a theme. and then them ultimately failing and humbling themselves. And anyway, so I really got into a lot of, I'll say, occultism and hermeticism, and learning about the tree of life. I had a Christian background, and so once I started learning kind of what the tree of life was, and the flower of life, and the fruit of life, and the egg of life, and all these fractals and numerical relationships between everything, and I got into the Fibonacci stuff and everything. It just went kind of crazy. But anyway, I got into all that stuff and just realized that this world is saturated in this stuff, this kind of hermeticism. And so anyway, when you kind of learn that, that's why I put together that part 6, is because when you kind of understand those relationships, all the stuff that goes on in the world just starts to fit into place, like why it's happening. Because I don't think anyone looks around at this day and age and is like, yep, all this makes sense. It's crazy. This whole thing is crazy. Everything on the news, like whatever you watch, it doesn't matter.
Yeah.
But when you understand kind of the tenets of what it's working under, it's like, okay, well, now that makes sense. That makes sense why it's being pushed. Doesn't make sense. Doesn't mean that thing makes sense at all, but it makes sense why it's being pushed. So anyway, I kind of got into this, and then I started noticing a lot of things about space and that I had never noticed before. And I started looking into quantum mechanics again and getting into all that. And I listened to the key point, I guess, or what really made me kind of start questioning everything, was there's this Isaac Asimov annual debate or annual kind of State of the Union that Neil deGrasse Tyson puts on from the Hayden Planetarium or whatever. And there's the 2000, I think it's the 2011 one. You guys, I encourage you to watch it, but it's about 3 hours long. But man, it's, you have all Brian Greene, all these people get up there and they start talking about what the state of quantum mechanics is and string theory and where we're at. And this Dr. Jim Gates gets up there and he tells everyone that for the last 15 years he's been studying string theory, and he's come to the point where he discovered that computer code from a guy named Claude Shannon is written in the equations that describe the universe, and that we likely live in a simulation or a matrix, right? So that's where all the kind of matrix theory and everything kind of started propagating. And I don't know, man, I just started listening to all them, and I'm like, okay, Copenhagen and multiverse quantum mechanics, and it just started to just become like a joke almost. I was just kind of like, this is ridiculous, So anyway, so to summarize the first 4 parts, and then I guess to tie that all back in and just finish up with how I came to all this. I was doing this thing on 9 and torus knots and Rodin coils and vortex mathematics and all that stuff, right? And I saw this ODD TV thing about 9, right? The movie number 9 or whatever. And I thought, well, that's interesting. I'll kind of hear what he has to say about it. And so he had some really great stuff about that movie. And then, so I subscribed to him or whatever and didn't think much of it. And then he comes out with this flat earth thing, right? And I'm like, okay. So I immediately unsubscribed, right?
Oh, man.
And I'm like, that's stupid. I'm like, I can't believe this guy had so much going for him, and like what a great, inquisitive mind he had. And he was able to break this thing down and blah, blah, blah. And so it just kind of wore on me, the whole flat earth thing after a while. And then I think in 2017 or something, I picked up Eric Dubé's book when I was going on vacation somewhere. And I just decided to read it. Like, well, I'll just see what they got, it's ridiculous. And that was it. Basically, after that, you're just like, okay, I can't disprove that stuff. So anyway, all right. So I might release a summary real quick, maybe within the next week or so, something like that. But this is the main argument to me, is that things get smaller with distance. Small things disappear, and then that small things disappear with distance, secondary to the compression rate within a given field of view. So that's kind of the first part, maybe diffraction in optics, and that doesn't take into account, that's just what's happening to the light after it hits an aperture, right? Either a camera or an eye. the aperture being a circular aperture of whatever you're using to observe the world, right?
Can I just say something there?
Yeah, sure.
When you talk about compression, Jose was on before on Nathan's today, and he spoke about it being a linear compression, and I disagreed with that immediately. I see it as it isn't a linear compression at all. It only happens up and down. It doesn't happen on the width. Obviously, things get smaller in the distance due to perspective, so that would be a linear change due to perspective. The further things go away, it should shrink proportionally. But the compression can't be linear.
So yes and no. So so when I say compression in this, I'm talking about the rate at which your visual field compresses the potential angles with which you view something. It's not the actual compression of something that you're seeing. So maybe I might have to show some diagrams of that, but the actual angular size of objects it's the rate at which they change subject to the horizon line. And where the horizon line comes from, and just think of this in terms of this is what I try to tell people. So if you're in a hallway, right, and you're looking off in the distance, you're equidistant from the floor, the ceiling, and the walls. You're right in the middle, and you're going to look down this hallway, and you're going to see the floor and the walls and the ceiling all converge to a point, right? That's your vanishing point. The vanishing point is not curve in that scenario, right? No one would argue that, right?
Well, to be fair, they have done in the past.
Okay, well, I can't. That's okay. I can't go anywhere with that one then.
Well, that was their argument essentially, and that's why I started to look into these optical effects last year. It was because I knew it was bullshit. I knew that what they were saying wasn't true. The inferior mirage was where the curve starts, and all this rubbish. I knew it was wrong intrinsically. Just
picture you're in a school, or you're in a university hallway, or a hospital hallway, or a whatever, right? The floor is coming down, the ceiling, or the floor is coming up, the ceiling's coming down, and the walls are coming together, and that's perspective, right? That's how we view the world, and we're viewing it off into a distant point that is coincident with our eye level, right? Which is the vanishing point. So you might have to picture a very long hallway but that's what occurs, right? The floor and the ceiling are not curved, right? They're straight lines. But
hey Travis, one thing I think Sonley was telling me yesterday, he's like, yeah, well, if this whole angular resolution thing is true, then if you're standing at the base of a skyscraper and you have a drone flying high up near the top of the skyscraper, then eventually the drone will disappear into the side of the building. And I'm like, yeah, I mean, assuming the drone is, of a certain size and it's of a certain distance, and it's right below the center of your eye level, then I think in principle it will visually disappear. And I think you do have a few slides in your presentation comparing using skyscrapers as an analogy. So would you say that a drone will eventually disappear into the building visually?
Right. So the example I gave was, so if you're compressing your visual field against a building, okay, so you are now looking up at an extremely tall. So again, when you do the calculations for this at 1 arc minute, you're going to lose roughly 2 feet at 1 mile. A 1 mile building might be kind of hard to find, but that's the rate at which it would occur. But if you compress your vision against that building, and your building now becomes your floor, right? Then as you watch someone ascend that building, right? Let's say it's a window washer. They're going to go up that building at a certain point. They're going to start to merge into the bottom of the building, and they're going to disappear building side first. So this is, so like Ranty, with your example with the wall, I've done the flashlight thing with the wall too. It's kind of hard to find a long enough wall that doesn't have any obstructions and it's kind of flat, doesn't have pictures on it or anything. But when you can do the same thing, if you get really close to the wall, you'll have the same thing. You'll have a far off flashlight or whatever it is. It will set into the wall, and it's just the same phenomenon. You're just compressing your visual field and creating a vanishing line. So
yeah, these guys were acting like it was so hard to believe that it could ever happen with a drone in a skyscraper. It's like I don't even know if they were being legit. Like, did they legitimately think that was supposed to be some kind of a debunking of this argument? It's like, no, yeah, in principle, that's probably what would happen if you had a drone flying really, really high up in some hypothetical skyscraper that's, God knows how long it has to be before the drone disappears. But yeah, it was just weird. I think they were just using that to kind of like distract and, deflect.
I mean, my example I gave in there was, someone would have to be at the top floor. That's kind of at your vanishing line, and they would wave their arm, out the window if they were essentially like a mile up or so. If they were if the building was a little bit less tall, it would be like, waving maybe 6 inches of their arm out, and you wouldn't be able to see it. It would still have set into your visual horizon at that point. So, yeah. So, anyway, so now picture yourself, you're in this corridor. Okay. And you know what, let's just go through some of that real quick. So let me escape from this. So the main things are things at smaller distance, small things disappear, and small things disappear with distance, secondary to a compression rate against which you're, pressing your visual field against a wall, a ceiling, a floor. It just so happens that floors are typically what we compress everything against, especially when we go outdoors, right? The ground is the floor. And then the second part is refraction of light, and this just kind of goes to what Dr. John Dee is kind of coining with this optical density increasing with height versus physical density across warmers, and that just goes to what emission, refraction, and things like that. So let me go to the first part here and maybe just kind of go through some of this real quickly. So Gavin from Vortex Plug, he's done some great stuff too. So if you want to check him out, he has some great stuff on how the eye works, and so essentially I took one of his videos that, again, we're looking through a spherical surface, but we as long as we're a certain distance away from the eye, a couple focal lengths out, you're starting to view the world linearly, and so those curves don't. So anyway, that's kind of that part right there. Then I just start building perspective, or building a corridor. That's all I'm doing here, is just building a corridor, and then the angles at which the closer things are going to hit your eye versus the angles at which a further thing is going to hit your eye, and noting that the angles are increasing as the thing gets closer. I don't think anyone that makes sense, right? So the angles increase as they get closer by, and they get smaller as they get further away. And when we model this in perspective, that's why the things closer to us are a little bit bigger than the things further away. And then I added in some parallel lines here along. So the top part here is like the ceiling, the bottom part's the floor. The paint stripes are along the wall, let's say, and then along the wall also we have some parallel lines, and those are what are going to end up becoming orthogonal lines when we model this in perspective. And so I just continue. Yeah, go ahead.
So does there become a limit? I can see that you're obviously looking with angles to the floor. Does there come a limit as to where all those angles will start to just merge into the same angle? So if you was to space them, so I'm assuming you're putting these a certain distance apart. Let's just give an arbitrary mile between each, the orange and the blue. So at some point when you get to maybe 25, 30 miles away, those angles will become indistinguishable between each of those mile markers, won't they?
Right. Well, so if you go back up to here, let's see. So you see how the red, blue, and green, each of those is an angle to the next stripe, right? So it's more looking at kind of your depth perception. But you can see the further you look out at a paint stripe, the further the paint stripe you're looking at, this angle is getting smaller and smaller and smaller, and it essentially starts to become very much like a straight line, which would be this straight line would be right through the direct middle of your vision. It's like your eye line, right?
Yeah.
So we're going to reverse this, though. I'm kind of modeling this somewhat crudely as like the light that would be hitting your eye from these objects. And then we're going to reverse this and kind of look at it a different way. But so here I'm kind of reversing these lines as if they were coming off of a point source, in this case, a light. So this light is emitting light in the according to the inverse square law, right? It's radiating out exponentially, okay, from a point source. And then your lens is taking that information from that light and reconverging it all at the same rate at which it came off the point source. And so that's why it's this exponential radiation is being then exponentially reconverged for you to view the world how it is, okay? So you're viewing a linear world, linear relationships, although the light that's being emitted between the observer and the object is radiating exponentially. So does that kind of make sense a little bit?
Yeah.
So once we do that, you can kind of start to see how we get this box kind of forming, right? So these are our paint stripes. We're now looking down this hallway, and you start to see the paint stripes get further away. They get smaller, and they get bigger when they get closer by. These radial lines that are going through here, those are these lines right here, right? Those are called orthogonal lines, okay? Does that make sense?
Yep.
And they're parallel. And so the perpendicular lines, or they're parallel to the floor and ceiling. The paint stripes are perpendicular to the floor and ceiling, right? And they create a second set of lines, and these are called transversal lines, okay? So far, so good?
Mm-hmm.
So radial kind of orthogonal lines and these kind of square transversal lines. In reality, these things are 90 degrees to one another, okay? Does that make sense?
Yeah.
Okay. All right. So what you derive then is, because we see the world linearly, right? This point, let's say this building now, it's a building. It's getting reflected light, and it's sending that reflection off exponentially. We're reconverging it exponentially. So it's, in a sense, we're seeing linearly. And so you see that the relationship becomes that the height is inversely proportional to 1 over the distance, or is inversely proportional to the distance. So what that means is that if I go, if I get, 50% farther away from something, it's going to reduce in size by 50%. Okay. And that's something that you kind of have to prove for yourself, I guess, or you can just take it for what it is. So there's a second way to, and I show a little, I'll go to this one here to show that. So if you just take a hallway, right, and you model a door out, and you model, you put your distance to that door, and you just mark it out, and you put it in a picture, and you scale it, right? So I just take this yellow line is this yellow line, this yellow line is these two, and this one right here is these 4. And at various distances is where I took the picture, and you see that as you double the distance, you half the size, right?
Yep.
Okay. So another way to view this this kind of compression, or how we're modeling the world, right? How we get from this corridor view, this orthographic view, right? Looking at either from the side of the person's head, or looking at them from the top of their head down. How we get from that to this kind of corridor appearance, which is what everyone draws in perspective, right? And so a way to do that is to model it kind of this way, where you kind of take this same view, let's say it's this upper one right here, and you kind of just collapse down the ceiling and collapse up the floor to meet the line, to meet the purple line in the middle. Okay.
This example, what you're doing now, is essentially one that I did today against Jose. I'd done it several months ago, and it was the first time I had a chance to actually put it out to anybody. And I essentially had Blackpool Tower, so you can see where you've got those where it says 10 feet,
right.
And you've got your angles looking at those blue and orange. Well, I was basically putting Blackpool Tower and then making it smaller the further away it goes due to perspective. And then you had the angles to it, and where this diffraction limit would be eventually, it would cut it off at the bottom. So It's essentially this. I can see where you're going with this. It's essentially the same sort of thing without actually talking about the diffraction limit. But yeah.
Yeah, it's a way to kind of show how these paint stripes get bigger with proximity and get smaller with distance, right?
Yep.
But there's still 10 feet. That's kind of my point of this one, is this 10 feet within this big old blue stripe is the same 10 feet in reality as this one over here. It's just smaller within perspective. So when you look in this 1-point perspective diagram, this distance to here is 10 feet, but this distance to here at the top is also 10 feet. So anyway, it may seem like a moot point, and I kind of made that point, I think, in the video. Like, this may seem like a trivial thing, but it seems to get lost in a lot of discussions. So Anyway, and then I just kind of model how we can go from one thing to the next, and we can model out perspective. So you go from your corridor here orthographically to a modified orthographic representation to flipping it around and looking at it from the back of their head, essentially, to this kind of a view. And so I then kind of start, I kind of leave that there where it is, and I start going into a little bit about how light is bent. And so the illustration is always either a marching band or kayakers or someone going through a prism. And you think of this prism as like thick sludge. And as the light hits this thing, it's going to, these kayakers here at the bottom, they get kind of caught up earlier. And these guys up at the top, they go a little bit faster. And the next thing you know, the kayakers are kind of going through at a downward angle. And as they exit, these kayakers at the top now hit the faster medium sooner, right? So they start going even faster. And these poor guys at the bottom, you know, they're still going slow, and the ray is bent down again.
And one thing I want to just say here, this is about terrestrial refraction, yeah? We're talking about, obviously, the way the light propagates over water, I would assume. But the globers have always acknowledged that upward refraction happens, except they think upward refraction lifts things up, so it looms them.
Well, no, they think it's downward refraction. So this right here is just an example. I can flip this prism upside down. I can flip it on its side. I can do whatever I want with it. And
yeah, but what I'm saying is they call it upward refraction, thinking it's making it loom. It's not. It's upward refraction that actually makes things go down.
Correct. Yeah. So if you have, so there's like emission refraction and absorption refraction. So the emission refraction is when the warmer air is around is making the air kind of less dense at the surface, right? So it's usually over large bodies of water because of the specific heat of the ocean, and right, they trap a lot of heat, so they tend to have almost always this emission phenomenon where the density layer is less near the surface, and then it goes up in height, and so that's upward refraction. Downward refraction is when you have a density gradient higher at the bottom, and it lessens with height. And in those cases, you're going to bring the visible world higher than it is. And so we'll get to kind of refraction and how I think that's been misinterpreted. But yeah, this is just kind of showing general what refraction does. It just bends light through a medium. It's a velocity change of light.
Keep jumping in. Tell me to shut up. You've got a presentation to do.
Oh no, you're fine. So again, we're just showing the same thing here. So then I just started to show how this becomes a convex lens system. And so there's a lot of great videos online where they show this becoming a much more gradual transition. I didn't want to go through all the headache of doing that, so I just stacked two prisms. But essentially, you get light refracting one way and light refracting another way, and they come and meet at one another at a focal point. Okay, so if they're coming off and they're hitting this lens, let's say, they're going to converge out at a focal point. And you can reverse the light and they converge at a focal point on the other side. And that's just what a focal point is. That's kind of why I wanted to define that. And so I take this prism example and I just say, well, now you just replace this prism with a convex lens. And that's what a convex lens is doing. And instead of these focal points right here, we're going to call them F1 prime and F1. And we're going to double the distance to F1, and we're going to call it F2. And we're going to double the distance to F1 prime and call it F2 prime. And that's what focal lengths are, right? So then when you want to model, we know from like Abbey criterion and other criterion that you need to have two rays converge through focal points in order to create an image on the other side. And project an image to a retina, and then that retina takes that information and pushes it through the visual, your optic nerve and through into your visual cortex, and then you perceive, right? You flip this thing right side up again, because what's pushed onto your retina is a real image. It's an inversion, so your brain kind of has to flip that thing back around again. And cameras do the same thing. I'm not entirely sure how they end up flipping them back, but at some point there's something in there. They flip the image upside or back right side up, so you're not viewing an upside down image. So when So you see the first ray is going to converge through F1, and the second ray converges through F1 prime. And you can, if you want to look at lens physics, you can just go to almost, YouTube has a ton of lens physics tutorials, I guess. So Khan Academy has some great ones. So anyway, but I don't want to get into the physics of lenses, because you can get convex lenses and thin lenses, and you can get all this kind of stuff where, you know, real and virtual images. And I just want to focus on when you're beyond F2. Okay, so you're looking at something far away. When you look at something far away beyond 2 focal lengths, which is typically around like a 35 millimeter for the human eye, and most 35 millimeter cameras and things. When you're looking at that image, it's going to project between F1 and F2. Okay, and this is behind your eye right here. So F1 is this convergence point, and it's converging this image and projecting it somewhere between F1 and F2, and then it hits your retina. Does that make sense?
Yeah.
So that's how things get smaller with distance, right? Because the angles through F1 prime and F1 start to get smaller and smaller. And so the point that they converge is getting smaller and smaller. And that's how this, you know, so this tree is the same size as this tree on the left side here, but on the right side, that's how it gets smaller with distance, you know, as far as what's being projected to your retina. Okay, so then I put the eye kind of into the scenario here. So now you got your eye, this is your lens, and here's your pupil. You know, your pupil's your aperture, right? So you get kind of a diffraction of light, and then it hits your lens and it gets converged. So is that so far so good?
Yep.
Just basics of an eye. So then there's ways you can kind of manipulate this, the light that's coming in, and this is called the accommodation triad. And I just kind of threw this in for that this is not a passive system. We can focus near to far, right? So we can, just like a camera changes its aperture size, we do the same thing with our pupil, and kind of a mechanism for how that occurs. So as we look at things far away, the lens gets thinner, right? And the pupil gets smaller. And there's something called the Helmholtz theory for how that occurs. There's other theories, but that's kind of the one that's I guess accepted. So the bottom line there is that to see something far, you have a smaller pupil and a thinner lens. So then I just kind of go through and just kind of start showing people how, as this tree gets further and further away, this angle starts to get smaller and smaller. So the aspects of the top of the tree are going to get smaller and smaller. And when you rotate, you can rotate this thing downward, and this phenomenon occurs throughout the entire length of this tree. Whatever the angular size of the tree is, you rotate these angles around, and it converges at a point, you know, along this tree base. And so I don't model that out, and I kind of wish I did, but that's how you view this entire tree at X distance, whatever that distance is. And so so I just kind of use it as a what do you call it, like a generic baseline, right? The top of the tree and the bottom of the tree. So we're going to look at the top of the tree. As it gets further, you see the angle is getting smaller as it crosses F1 and F1 prime, and our tree gets really tiny, okay? And it's getting closer to F1 between this distance here between F1 and F2. So this is kind of the conclusion of part 1 for the most part, and then I just kind of sum things up. I'm just kind of laying the groundwork, you know, for some of the lensing and the perspective views, just kind of defining things, how we're going to go forward. And then I just get a little bit into the issue of the horizon rising to eye level, which is always the topic of great contention, right? Whether or not the horizon rises to eye level. This was one of the first, I guess, things that I did when I was trying to figure out if this was true or not. Was I took a phone onto a plane, and I just put it out the window, and I wanted to see if at 300 feet I was still looking at the same piece of land, you know, relative to a marker, right? You can't just use the plane window. You kind of need a wing or something like that to have as a reference point. And so I did it, and I was like, okay, it doesn't seem to go down really. And so I had some caveats to that, because I did it a couple other times, and I found that it did go down. And I was like, man, maybe they're right. Maybe there's just, it is a round Earth, right? So here's something that I just thought was pretty interesting. So here's some of the times I had done it, right? So as you can see, right, you're here, what are you, maybe 300 feet off the ground here? And up here you're at 30,000 feet. The level of where the sky is meeting the ground is the same for all of them, okay? And the way I standardized this was you can either tape your phone to the window, or in this case, I think there was an exit row like shelf thing I could set it on in the exact same position each time. And so that's how I did that one. Assuming again that the plane was level. I don't want to get into that whole argument, but it was level. So then you can use like a theodolite or whatever. You can do the same thing, but you get the same phenomenon.
So when you was on this plane, did you keep feeling the nose of the plane being dipped down to go around the curve?
Right. No, I know. I gotcha. It's kind of crazy. And so anyway, but this is a very interesting. I kind of was racking my brain over this. Like, how is the horizon dropping? I think Scientism did a video a couple years ago where they were up in a plane and they were like, well, it does appear to drop. And they were talking, and they kind of threw out terms, you know what I mean? And this is kind of why I put this together too. I think we talked about it before we went on, was diffraction and angular resolution, and it's the refraction of light and all these things that do have defined parameters, right? So I kind of wanted to do this to get everybody on the same page for what we're talking about. And I think it was when Soundly did the bridge live cast or whatever, somewhere around New Year's. I think it was Anthony. He got out and was debunking it, but I think we're kind of conflating some terms, you know. And so I got on with Nathan. I was like, Nathan, I think we need to like just define some of the terms so that we're not kind of just throwing the stuff out there. And so he kind of summarized it the best way, I think. And I was like, that's spot on. That's exactly right. So diffraction is what's occurring after to the light after it hits the aperture, right? And refraction is what's occurring to the light prior to it hitting your aperture. Okay, so does that make sense?
Okay, so you would say that the fraction limit is an angle.
Well, I don't think there's a refraction limit. There's a diffraction limit.
Yeah, that's what I said. Diffraction
limit.
Okay,
sorry. Yeah, a diffraction limit is this angular issue. This angular resolution limit is the diffraction limit. Diffraction occurs, I'll get into that later, but diffraction is just kind of like ripples in water, right? That's diffraction patterns. But when you get into Rayleigh criteria and everything, that's where the formula arises for what the angular resolution limit is across patterns that are diffracting. So we'll get into that later, but getting back to this thing. So I saw this, I saw the horizon drop in one of my little like experiments, I guess you are, not experiment, observations, right? So I'm like scratching my head, like and then just, when I was doing this video, I started to look back through this stuff and I was like, man, if you look at can you see the wing markers on here?
Yep.
Right? In the black lines where I'm pointing with the blue arrows.
Mm-hmm.
So you see how as the horizon drops, the wing gets closer to the window, right? You see the markers on the wing. The black line is where that corner, that flap is. So as this horizon drops, this flap is getting closer to your window.
Right. Okay.
Do you see that?
Yep.
So I was like, well, that's lensing, right? That's a convex lens. So when I just grabbed a cooking lid and showed how this occurs, right? So you grab a cooking lid and you put it against your backsplash or whatever, and you see how this cooking lid distorts and brings this apparent horizon, in this case, lower, but it also brings these little cooking prongs, right? Your stovetop, it brings them closer, right? So it artificially drops a horizon and artificially brings things closer in. Does that make sense?
It does, yeah.
So I looked at Wolfie's, he had one on horizon drop from an airplane window. And so I'm looking at this thing and he has there's a couple issues here, which I think, I'm not sure, I don't know why this was overlooked, but so airplane wings are built to flex a little bit, right? And their wingtips rise when they are in flight. Okay.
Well, I see, because it's supporting the weight of the plane, isn't it? So at the
Well,
edges, at the most flexible part, will essentially sort of lift up.
Right. Well, I'm not a pilot, but essentially what's happening is that it's like a mechanism for not having something too rigid. It needs to be able to flex as this plane goes through like turbulent air and things like that. These wings can't be terribly rigid, right? Or else there's going to be some stress and they're gonna break. And so they have to be able to bend. And so the amount of bend is greater at the wingtip. So that was my first inclination. I was like, well, maybe this wing is flexing so high that's why I'm seeing these things brought closer, right? So, and again, too, in Wolfie's one where he shows the horizon drop, look at this black smudge here, right? Do you see the black smudge right above the red arrow? And I kind of outlined in relation to this black smudge where the flat markers are,
Yep.
right? And that's when he's high up. And then when he's down on the ground, you see how much further, that's like 3 to 4 feet difference, right? Mm-hmm. To the wing is essentially demagnified, right? And you see how the wingtip is bent downward, right? Anyway, so I went and looked at a bunch of footage on how wingtips flex and everything. And what you notice in almost every single one of them is that the proximal wing flexes very little, right? And that makes implicit sense. You can't have this proximal wing where this engine is constantly flapping up and downward, like a bird. That doesn't make sense. It's all in the wingtip, essentially, is where this flexing occurs. Does that make sense?
Yeah.
Okay. And so here the Boeing, it's landing, see its wingtips right before it lands, and then right when it lands, they drop, right?
We've actually got Wolfie's right-hand man in the chat right now. He's called Airline Pilot Research Global Airlines, and he's just put 2 words: "Oh snap!" full stop. I think he's just got it.
Well, I don't know, but my point with this is just like, is you have to take into consideration this lensing phenomenon, and when you use wings, you have to take this into consideration when you're evaluating some of this stuff. So here's just some examples of this wing rise. So if the wing rises, right, your horizon level can't be matched against that wing anymore. Anyway.
What you did essentially was look for reasons as to why this. You didn't just take it on face value and say, okay, the horizon seems to have dropped, we live on a ball, end of story. You actually went into it, you looked at the plane design, how it's all made, and then you came up with an idea that essentially the wings aren't as rigid as you first thought and can't be used for this type of the horizon always goes to eye level.
Well, no, what I did was I just had several observations. Like you increase your data set, right? And you just do this several times. And what I noticed was that sometimes on some planes, for whatever reason, and I don't know why, I think and I think I explained it a little bit in the video, but there's typically 3 panes to these windows. And so as the plane gets, so in this case, let's go to this one here, or was it right here? So in this case here, the panes seem to flex and they bow outward. I don't know if that's the middle pane. I wouldn't think the outer pane would really do that as much, right? With cabin pressure, but it seems to occur with cabin pressure. So as the cabin pressure increases inside the plane, this bowing outward seems to occur, and it drops the horizon and brings the wings closer.